Now let's come back to A equals RB. The encyclopedia A in black hole number 1, or left-hand black hole here, is encoded in the radiation in region 2 over here. Our problem before was that sounded crazy because somebody manipulating the radiation over here could perturb what's inside the black hole in just such a way that somebody who jumped into this black hole over here would detect that a very, very distant observer had done something to this group of photons over here. That sounded outlandish. But now we know that if these photons over here are entangled with the black hole, which they will be, that an Einstein-Rosen bridge, and from outside you can't see that Einstein-Rosen bridge, but the Einstein-Rosen bridge will open up. And so anything anybody does over here will affect what's behind the horizon of the original black hole. In other words, A equals RB makes perfect sense. Again, it has to do with this basic idea that information is not where you think it is. This is a radical example of it. What about the wormhole side of it? How can it be, why should it be, that somebody who goes into one black hole in Alpha Centauri can't get through the wormhole and come out? Well, one end of the wormhole is in New York, the other end is in California. Think of it as a tunnel between the two places. Why can't you drive through that tunnel? And the reason is that Einstein-Rosen bridges, and this is a gravitational phenomena, tend to stretch and expand with time. That's the solution of Einstein's equations, gravitational equations. Wormholes grow. So, who was it, Franklin? I can't remember. Franklin or Linus. If Linus tries to drive into the New York side, he will encounter the fact that the wormhole is growing. And in fact, it will grow so fast that he cannot outrun the growth of the wormhole and will simply never get through to the other side and come out the other side. That's the non-traversability of wormholes. You can't even send a light signal through because even a light signal will not go fast enough to outrun the growth of the wormhole. That's the gravitational side of it. Is there a quantum side of it? Yes, there is, and I don't have time to tell you what it is. I will tell you what it is. I don't have time to explain it, but I'll tell you that it's a computer science concept. It's called the growth of complexity. The black hole, quantum state of the system is becoming more and more complex. It's very much like this information scrambling that we talked about, having to do with falling. The quantum state of the wormhole evolves, it becomes more and more complex, and that complexity translates into the growth of the wormhole. So these are all these very, very remarkable correspondences which tend to make us think that not just that there are deep connections between quantum mechanics and gravity, but it's at some level, as I said, I'll say it again, they're two sides of the same coin. Okay, so we have the idea of a quantum hologram encoding information which could be far from where the object that it's encoding is. And what is the other side of the coin? The other side of the coin is gravity. I like this picture. It's my favorite one of all. There are criticisms. Oh, incidentally, one might point out that most of these ideas grew not just out of a combination of quantum mechanics and gravity, but string theory. How string theory got into it, I haven't really said very much about. But let me tell you that all of the precise examples, all the mathematically precise examples of this correspondence tend to come from systems which were invented or discovered in string theory. Of string theory, quantum gravity has been the victim of an enormous amount of criticism. The criticism, which are, first of all, things unjustified, but what does it have to do with? The criticism, I would say, stems from the fact, and I think it is a fact, that good science almost always spreads its influence far and wide into many fields of not just physics, but even outside of physics, and in particular, into engineering, into technology. And that's a pattern that we've seen over and over and over again. Special relativity led to nuclear energy. General relativity, we use it for navigation by satellite, believe it or not. Quantum mechanics, the list of technological advances. And quantum mechanics was not invented by people trying to do technology. It was invented by people who were curious about the atom. Quantum mechanics, among other things, it led to the MRI machine. But so many things that I have that the list would go on and on. Quantum electrodynamics, trying to understand the quantum mechanics of electrons and photons, in particular photons, led to the laser, or at least is closely connected with the laser, and so forth and so on. What about quantum gravity, general relativity, and its connection to quantum mechanics? It seems so infinitely remote, with no connections or applications to the rest of science. It could be that that's true. It could be we're just stuck with that. But that has not been what is happening. First of all, these connections between quantum mechanics and gravity have led to new insights into strictly phenomena which seem to have nothing to do with gravitation. For example, the surface of a black hole, the horizon of a black hole, behaves as if it were made of a fluid. That's something that general relativists discovered a long time, but not just a fluid, but a quantum fluid, whatever that means. One can use the fact, by knowing enough about black hole physics and knowing enough about general relativity, you can compute properties of fluids that were too hard to compute otherwise. Here's one example of something that was inspired by the connection between fluid mechanics, black holes, and quantum mechanics. It's a bound on the viscosity of fluids. Now, that doesn't seem to have anything to do with either of those subjects. Well, it's a little bit quantum mechanical. It is quantum mechanical. Eta is the viscosity of a fluid, the stickiness of it. S, on the right-hand side, is the entropy per unit volume of the fluid, the heat per unit volume. What was discovered? In the context, not discovered by people doing fluid dynamics, people comparing properties of quantum mechanical black hole horizons with fluids, is that the viscosity is always greater than equal to some number that includes h bar, that includes the quantum constant, times the entropy density. Will that have impact into fluid dynamics and into, probably. There are things called strange metals. Strange metals are a form of matter that was discovered by condensed matter physicists. Are they important in technology? I don't really know, but they were discovered about 30 years ago, and they were metallic systems which behaved just differently than ordinary metals. It's turning out that those strange metals are mathematically identical to certain special kinds of black holes called extremal black holes or near extremal black holes. Both sides are quantum mechanical. One side is also gravitational, extremal black holes. The other side is the pure quantum mechanics of certain materials. Information scrambling, the thing which I told you accounts for the falling of the apple as it accelerates in the gravitational field. Information scrambling is an important thing in quantum computer science. The information scrambling from black holes led to a bound, again another bound, that a certain constant called the Lyapunov exponent in information scrambling is always less than some other constant. That now is considered a reliable fundamental bound on how fast information can spread through a quantum mechanical system. I told you that Linus cannot get through the wormhole. Well, I was a little bit too pessimistic. With a little bit of help from something called the exchange of classical information, these little purple dots being sent from one side to the other, that's just ordinary Morse code, for example, but has no information about Linus or about anything else inside the wormhole, with a little bit of help from a little bit of classical information, you can slow down that growth of the wormhole. You can slow it down enough so that indeed Linus can get through it. That phenomenon, which was discovered in the context of gravity and quantum gravity, has led to a new protocol and new experiments for quantum teleportation. Quantum teleportation is a real thing. You can teleport information. What it means, you can't exceed the speed of light, but you can send information in a way that is completely hidden, 100% hidden, cannot be decoded by an eavesdropper. And so it's led to new protocols for quantum teleportation. Experiments are now being done to confirm that this can happen, not in black holes, but in quantum computers. I'm not allowed to tell you that the experiments are successful because I promised not to mention that they're being done and that they're working out successfully, so I won't. Quantum complexity theory, the growth of wormholes, the whole idea of gravitation being controlled by the growth of complexity has led to many new insights into how complexity of quantum systems evolve. We've seen advances coming from gravity in error correction. Error correction is the big hang-up in trying to build a quantum computer. It's too easy to make errors in a quantum computer. You have to error correct for them, and a whole new insight into error correction has come from thinking about gravitational systems again. And finally, in the hands of one of my favorite physicists, Juan Maldacena, much of what we're talking about has had a very interesting influence in cosmology, in inflationary cosmology. So far from being a totally isolated thing outside the framework of any other science, this quantum gravity is beginning to have an effect, which, let's just put it this way, condensed matter physicists and quantum computer physicists and theoretical cosmologists are being forced to learn what ADS-CFT means. And they are learning it. They're learning it and using it. So this is exciting. This is a very, very exciting period in the development of physics. It is also one which is very, very difficult to explain to a general audience. You know, when you give a lecture like this, or what did Lincoln say? You can please half of the people, half of the blah, 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 the time. Well, you can please half of the audience, half of the time, and so forth and so on. I think the real truth is, in a lecture like this, you're lucky if you can satisfy any piece of the audience even a little bit, because the ideas are complicated, they're difficult, and so forth. You do your best. You do your best to try to explain, and I've tried to explain as well as I can. I hope you have gotten something out of it. I hope there's at least one person who has gotten something out of this lecture, and I thank you for listening.